Hi guys, how's everyone going? So today we're going to be talking about protocol wars. It's like Star Wars, but even geekier. Before I start talking about all the different protocols that are available, I'm going to start by telling you a little bit about Radix. So my name is Piers Ridyard. I am the CEO of Radix. And Radix is a public ledger, decentralized ledger technology, right? And in essence, it is deliverable. We deliver scalability it is scalable, developer-friendly, and easy to use. Our mission is to provide developers with the very best tools to build and deploy decentralized applications, tokens, and coins. And our purpose is to give anyone, anywhere, friction-free access to the digital economy. So, what I want to cover in this talk is, first of all, what is this battle currently for? What are the stakes and why are we fighting it, and what is actually the protocol wars that are going on right now? Why scaling these ideas is difficult, and then what the choice of paths we have going forward are. So the battle. A long time ago in an economy far away, specifically 2008, a group of individuals and a specific individual called Satoshi Nakamoto came up with this idea of Bitcoin. Now, Bitcoin came out of the cypherpunk movement. And Bitcoin was designed to be money, but different. The first important factor of it was that it was incorruptible, that you had a known amount of currency and that you couldn't have a central authority deciding that suddenly that there could be more of it, that it was unstoppable. And unstoppable means that you can't, essentially that it's censor resistant, that it's anti-fragile, that as more people join the network, it becomes harder and harder to stop the network from occurring and makes it more inevitable as a system. And the last point was the really difficult one. That was actually the most difficult of all of these. It was the anonymous bit. And what anonymous means from this point of view is that you can just join the network without having to validate who you are, without having to prove anything about your identity. You could create a cryptographic identity, and that was strong enough for you to be able to do things within the network. So who were the cypherpunks and why were they important? They have this idea that privacy is necessary for an open society in an electronic age, that we cannot expect governments, corporations, or other large faceless organizations to grant us privacy. We must defend our own privacy if we expect to have any. Cypherpunks write code. We know that someone has to write software to defend privacy, and we're going to write it. And that was in 1993. And with things like the Facebook stuff with Cambridge Analytica and sort of more and more control being held by these centralized organizations, such as Google and Amazon, and Apple and Facebook, it was very prescient to write that back then, but the idea of sort of privacy was something that was still very in its early phases. But what this created, what Bitcoin created, what blockchain created was this really interesting toolbox that we can now reach into as developers and builders and entrepreneurs and use these tools in many amazing applications. And this toolbox incorporates strong encryption, pseudonymous identity, proof of control, and unique digital objects. And I call these like the 4 pillars of crypto. So strong encryption. Your wallet is also your public key. Your public key I can use to encrypt information and send it to you. And then you can decrypt that with your private key. So not only have we got this system of being able to send money to each other, we've also created one of the world's biggest cryptographic key exchanges for us to be able to send encrypted information to anyone from anywhere. Pseudonymous identity. This means that I can have a choice of privacy, that I don't have to prove who I am in an identity sense in terms of who I am right now as a person to be able to interact with the network, that I can choose to reveal or not reveal that information which is incredibly powerful from the point of view of personal privacy and your choice to do what you want to do with your identity. Proof of control. This is being able to generate a signature against the public key and saying, hey, I control that address. So everything that comes with that clearly belongs to me. But again, this is the choice to be able to do that rather than the requirement to do that to be able to use a system. And the last part is digitally unique objects. And this is the basis of money, right? If we can create a digitally unique object and we can prove that there's only one of them and we can send them peer-to-peer to each other, hey, we've invented the idea of digital money. And the last concept that sort of brings this all together is this idea of digital sovereignty. With those 4 key tools, we now have the tools available to us to be able to own digital unique objects, to be able to own our data, to be able to own our encryption keys, and be able to control who and how we deal with other people in a digital fashion without revealing a huge amount of information about ourselves. Now, that's the baseline challenge. Like, everything else on top of that, with KYC, AML, that's fine, but this all comes back to the idea of the Cypherpunk Manifesto being privacy should be a choice, and you should be able to do that in anything that you do online. So the challenge is how blockchain is built. As an architecture, is a really good architecture for solving the Byzantine generals problem. But it also has a problem in that every time there is a block that is created, you put transactions in it, and everyone races to get the hash, to be the first person with the most number of leading zeros to get the Bitcoin. And then that hash and that block then leads on to the next block, which then leads on to the next block. Now, 2 or more hashes which fulfill the boundary condition may be created at the same time with a block of transactions. And so the network then has to choose which one of those is the best fit for the boundary condition. Now, that's fine whilst you have a small number of transactions. But as the network gets bigger and you need to put more and more transactions into this block, you end up getting to the point where the information can't synchronize around the network fast enough. And so you get this thing called block thrashing, which if we removed all of the block size limits today and relied on just the best internet connectivity between all points and still kept it as a decentralized network, would give us a throughput of about 500 transactions per second, which just isn't good enough for mass market application, not even close to being good enough for mass market application. We've already seen that with things like CryptoKitties, meaning that the entire Ethereum network sort of fell over for a bit. So you can then go, well, what if we just split it up and we say, these nodes over here, they're going to do some, and then we'll say, no, these nodes over here, they're going to do some. And so we'll have 2 blockchains where half of the miners are doing one side and half of the miners are doing the other. But you've split the attack vector, right? It was a 51% attack, it's now a 25% attack, and then if you split it up again, then it's 17.5, and it gets smaller and smaller. So then comes this idea of a new architecture. Let's change the architecture and use something called a directed acyclic graph. And directed acyclic graph is a really interesting new architecture. Well, it's an old architecture, but one that people are starting to look at a lot more now, where you have these tips. And at the end of each tip, a tip is a transaction. And I just have to verify 2 previous transactions to allow me to have my transaction on the network. And so I don't have these block size limits because I'm just waiting for the transactions to go through. But you still have this limit of total throughput of the network, because once you get to a certain size of a database, you just can't process transactions quick enough for a single server, a single computer to be able to do it. So what do you do next? You shard it. You cut it in half, and then you allow some nodes on one side to be monitoring some of the tips and some of the transactions, and some nodes on the other side to be doing the other ones. And DAGs shard really easily. They're really nice architecture for doing that because they're sort of an unstructured data structure. But you may be able to see a problem here. If my balance is here from my last spend, and then I want to spend my next spend, and I get to pick which tip I put it on, then I can put it here on this tip, and the nodes on that side of the shard can go, yep, I can see the transaction history, I can track that back, that balance is good, that spend's good. But I can also put it on this tip. And that also goes back to my other balance. So suddenly I have a really easy way of doing a double spend on a DAG. And that is the problem that has to be solved, that people are trying to solve right now. And they're solving it in some interesting ways, which I'll come to. But essentially, this brings us to the DLT trilemma, or the blockchain trilemma, which is that you have decentralization, scalability, and security, and you've got to pick 2 of them. You can't have 3 of them. So decentralization means that if I have any node on the network, I can have a node that doesn't have enough resources to manage to do all of the transactions on the network, but can still be a productive member of the network, right? Doesn't have to be able to do everything to be able to be part of it and be useful. I then have scalability, which is that even the most powerful node on the network doesn't have to be able to do everything. I can add more nodes to it, and it can increase my throughput. And so if we look at something like Ethereum, that's 20 transactions per second, that's not too difficult for even your desktop computer to do. But if you start looking at something like Visa, which is 54,000 transactions per second, the average server can do about 2,000 cryptographic transaction verifications a second. And so once you get past that, you start to need to cut up the ledger and add more resources horizontally to be able to scale it. So even Visa would need a minimum of 27 servers to be able to do its throughput without any duplication, without any redundancy, and Alipay a lot more. So if we're looking at mass market scalability for even a single application, you're suddenly looking at really needing to be able to do both scalability and decentralization. And the last one is security, which is saying that if I split up the ledger, can I have a way of not also splitting up the attack vector and making it easier to attack a certain part of the network? And this is the real tricky one. If you're going to make it decentralized so that a single node isn't processing all of the transactions on the network, how can we make sure that that also doesn't reduce the total attack vector of the network? So there's some interesting solutions that people are looking at the moment. And I've split these into 4. The first is a master chain. Second is a delegated authority, or master node organization. And the third is a potential new architecture, which is sort of where Radix comes in. So the master chain is saying, hey, look, we've got this blockchain, and it's working really well, and we've got lots of miners, and they're validating the transactions against it. So why don't we create some subchains, some off-ledger transactions that we have ways of validating back to the main chain? And this is really interesting. This is what Lightning is. This is what Raiden is. But it also has the problem that the main chain still isn't scalable, right? You're taking a load of things off the main chain, but you still have that upper bottleneck. And while we're talking of a few thousand transactions or even millions of transactions per second, that's fine. But if we want every single person in the world and every single device to be able to use it simultaneously, there is still that bottleneck. It's still going to get to the point where this architecture still doesn't work. The second is to say, well, why don't we just create a central cabal of nodes that we know and trust and that they can all synchronize up together, and then everyone else just syncs up with them and is able to audit them, but they're not directly responsible for the full consensus of the network. But this is really going back to this sort of centralized trust authority. It's going back to this idea of having a center to the network, of having a single corporation or a bunch of corporations that this relies on. It takes it away from the original concept of creating a network that anyone can join and everyone can be part of, and makes it a choice where some people are in and other people are out. So how do you get this? How do you solve this trilemma? How do you bring something together that can be decentralized, scalable, and secure? And the way that we did it in Radix is we sort of took it from the point of view of not saying, well, how do we solve the problem for just the number of transactions that are happening today, but instead looking at what the end state is going to be. And the end state is going to be every single person, every single device needing to use some sort of protocol that they can all communicate and do their transactions with each other and do smart contracts with each other without there being any bottleneck. So if that's the end state and you're storing all of this information about all of these transactions and all of these smart contracts, then you need to think about a data structure that actually echoes that. And it's not all going to be one database. It has to be sharded. In fact, it has to be massively sharded. So what we did at Radix is we said, well, let's just start with a sharded architecture. Let's design an entirely new data structure and consensus mechanism and base that around the concept that we know where we're going to get to. Just every single person, every single device needing to use a protocol simultaneously. So let's design the concept of what that space is going to look like to start off with. So we created 18.4 quintillion shards, which is a very large shard space. And it's so large because we were like, well, what happened if we were storing all of Google's data and all of Google's throughput? What would that look like on 18.4 quintillion shards? It's about 2 megabytes a shard. And the reason that you set the shard space is because if you set the shard space right at the start, you don't have to adjust anything. You don't have to have overhead for cross-shard chatter. You can say, all right, this is my public key. My public key determines the shard I live on, and it will determine that shard from now until 1 billion transactions per second. And so I don't need to look across 18.4 quintillion shards to see if you have double spent your transaction. I just have to look on the shard you live on, and you will always live on that shard. The next thing you do is once you have the sharded architecture, you can create an overlapping node map where nodes of differing amounts of resources can manage the throughput of the network. So you can have a Raspberry Pi doing some of the shard space, and you can have a much bigger server doing a lot more of the shard space. It creates this overlapping map that allows this massive throughput where you can still have a high degree of certainty in the validity of transactions. And that's where the last bit comes in, which is Byzantine fault tolerance versus Byzantine fault detection. So most consensus algorithms at the moment are what's called Byzantine fault tolerant, which means that if there is a fault, the network will accept faults up to a certain point, and then once it's over a certain point, you can kind of change the network's mind about things. So this is the longest chain, this is the longest chain, and then suddenly another chain races up behind it, and so after a certain point, 51%, everyone goes, okay, now this is the longest chain, so I believe this is the history of truth. Even if everyone had been agreeing up to that point that another history of truth was correct. What Byzantine fault detection does, and what we do on Radix, is we enable it to be possible to detect if someone is lying about historical events. So instead of having to have everyone constantly vote on what the truth is, it is now possible to prove if someone is telling a lie about historical transactions. And that means that even on shards with a high number of dishonest actors, we can still reliably make sure that the truth about a transaction is always the thing that wins out, and that a double spend is not possible even at high numbers of bad actors on any given shard. So, my parting thought on this is just along the lines of what are we doing this for? Why are we building this? And I like to talk about whether or not you're building a platform for the world to build on, or something for a corporation to benefit from. And a lot of these solutions that we're seeing at the moment with things like central authorities end up crossing back into this line where we're saying, hey, this is a group of people that we're going to benefit, and then everyone else sort of doesn't get into that club. And what we really believe with Radix is that everyone should be able to benefit from an architecture that is going to be important for everyone in the world at some point. Everyone should be able to join it, participate in it, benefit from it if they are useful to the network. And that there shouldn't really be a barrier to entry for that. You shouldn't need to buy your way into it, or you shouldn't need to have massive amounts of serving power. And that your choice to join it or not join it should just be based on the fact that you can generate a public-private key pair and be able to ping the network. Thank you very much for your time.
Are there any questions here for Pierre? Here in the middle.
Thank you. So My question is about the Byzantine fault detection, and I didn't really understand how it exactly works and how you could detect the faults, well, the nodes that are lying, and also how do the nodes that work for each shard are split? How are they split? Is it something random, or is that something depending on the number of the nodes who are using the network, or how is it split?
That's a very good question. Both of those are very good questions. So the first one is how do we do the fault detection rather than fault tolerance? So the platform is a gossipy network, which basically means that every time a transaction comes into a shard, all of the nodes will gossip with their other shard mates what transaction they've seen. And if this transaction hasn't been seen before by a node, then they have a little clock counter inside the node, which is called a logical clock. So every time a transaction comes in, they'll be like, have I seen that before? Check it against their local database. They go, oh, no, I haven't seen this before. So I'm going to add this to my database, and I'm going to add my logical clock counter. I've increased it by 1. So let's say that this one was transaction 5 for this logical clock, this one's transaction 6, and this new one is transaction 7. Now, what's really important is all of the different nodes can have all different logical clocks, right? Because I may have just joined the network, but someone else might be on logical clock 10,568. So it's a local view of what the time of events that have occurred for each of those nodes is. So what happens next is you then gossip out to everyone else this new transaction that you've seen. I haven't seen this before, so maybe everyone else hasn't, so I'll tell everyone else about it. And then periodically, you also make commitments about what you've seen so far. So you take your database history of events, and you create a Merkle tree off the back of that. But with your Merkle tree, you're also creating the order of events that you've seen. So you're putting your logical clock value against each of those events in each leaf of the Merkle tree, which means that periodically, let's say that every 5 transactions, I will say I will also gossip my current commitment, and my current commitment will reference all previous commitments, right? So there's no way of me lying about what I've seen in the past, because I'm constantly telling everyone what my commitments are, and that and anyone can come along and make sure that I am able to validate that that commitment led from the previous commitment, and I can see that all those transactions were in it, and that I can also see that you have basically given me an unbroken chain of the truth of events that you've seen from your point of view. So the way that a double spend would work on the Radix network would be one of 2 ways. One is you submit 2 transactions that are conflicting simultaneously, right? So what we have is we have this concept of finality time. And the finality time is based on a very large number of nodes being on a shard. So let's say 1 million nodes on a shard. That's not across the entire network. That's just one shard. 1 million nodes on a shard. And we base finality time on the time it takes to gossip across a lossy, bad connecting, 1 million node network twice. So a transaction starts one end of it, goes all the way to the other end, and then comes back again. And that gives you enough time to make sure that if any conflicts are seen within that finality time, that they can just be dropped. You say, these spends, they conflict, but they're within finality time, so I'm just going to drop them. That's why you have to wait 5 seconds to be absolutely certain that a transaction is good on Radix. The other side of it is someone trying to present an earlier conflicting transaction to a later transaction, right? So you go, oh, by the way, this transaction that everyone now has and has gone past finality time, this earlier one, this was earlier, so I'm just going to put that into the network. The thing is because of your commitments, you can't do that, because I can audit any of the commitments you've already sent around the network to prove that that was never part of your history. So you're lying about it. And then we can spot a false transaction very simply. Your second question was about whether or not the nodes are randomly assigned, or whether or not there is a logic behind that. There is actually a lot of logic behind that. I don't want to go into it too much, so you can come and have a chat to me afterwards, because it is a little bit more technical than what I've already gone into. But essentially, nodes get pseudo-randomly assigned where they start on the address space, and then they can take as much of that forwards as they want, and that all the way around to the other side again. So that means that they can do the entire address space, or they can do a part of it. And then nodes will also optimize how they, which shards they manage, because the less nodes on a shard, the more fees that you earn from that shard. So you basically have this self-leveling effect where nodes are like, oh, okay, so this shard group or this shard over here hasn't got many nodes, so I want to go there because I'm going to get more fees, I'm going to get more reward for doing that. So part of the incentive mechanism also makes sure that there is always good coverage on every shard and shard group in the network.
Thanks. I noticed that we have one more question.
Thanks. So I really like the idea of designing the whole system from the end state. I think that's really cool. But how do you actually test that? So you said, you're expecting this end state with so many billions and you have 2 to the power 64. How do you actually test it? And how far are you guys along between concept and, which is looking very good, to actual implementation? How far are you on?
Another great question. So we test it in several stages. The first stage is just finishing and the next stage is about to start. So the stage that we've started with is creating a way of programmatically spinning up large number of nodes across a number of different cloud service providers, and then just spamming the network as much as we can with as many false transactions, network splits, checking to make sure that, putting in loads of double spends and really seeing what happens when you have a few billion transactions a week going through a network of that type. And that's really where Dan started. Dan, who's the founder and CTO, that's where he started with this in the first place. He took the Bitcoin blockchain back in 2011, 2012, forked it and tried to break it and found all the problems that came out from that. So basically the team has a history of really checking to make sure that the throughput is good. We have got to, our last test was 20,000 transactions per second. We're planning to do a 50,000 transaction per second one shortly, and then we'll be ramping that up to 1 million transactions per second. Although that is across our private test network, all of the transactions themselves will be publicly visible, and you can audit every single one of them to make sure that they have the full signature scheme, to see whether or not how many nodes they went through when they were verified. All of that kind of information will be publicly available. The second part of that is our test network, our alpha developer, our developer alpha, which will be going live in the next month. You can currently sign up on our web page at radixdlt.com/developers. And this is essentially giving developers the tools to go and test our network now, even in a really early phase, and let people in the wild come and try and break it and test it in ways that we hadn't foreseen, because obviously you can't foresee everything. So it's really important for us that we get it out as early as possible and start getting people playing with it even before it's a live network, even before we do our public launch.
Thank you. I hope that answered your question. One more question? Here.
Okay, I can see, I think conceptually that each shard is like its own blockchain. More or less, right? You've got your address there, and whatever you do there is not going to be double spent. You could have it two addresses on 2 shards, and they have their own little balances. Now, but then you showed a slide of something that I would call master nodes, and I'm probably wrong, but something where do they all really combine into one master chain at some point?
So there isn't. So the output of a shard is considered overall valid by the other shards. So it's not a master node itself. Because of the way that the spend has to originate from a single shard, you just need to check on that shard if there's a double spend. If there's no double spend on that shard, then it's a valid spend.
It doesn't leak into other...
It doesn't leak into, but the output of one shard is the input of another shard, right? So there is no overhead, there's no overhead cross-chain chatter. All you're basically doing is because of the largeness, because of how big the shard space is, 18.4 quintillion shards, the probability of any given transaction being on the same shard is 1 in 18.4 quintillion, right? So transactions will always be crossing from one wallet to another. And that means that you need to involve the nodes on both of those shards to do that transaction. So you need at least the nodes that are covering both of those shard groups to be involved. But every time you have a transaction, that could be different nodes across different shard groups.
So almost every transaction will be from one shard to another shard.
Yes, exactly. So Radix is a fully state sharding solution. So we are able to do cross-chain for not just transactions, but also for smart contracts as well.
So then I think what you're saying is then there is a master record of all transactions.
Yeah, so if you combined all of the nodes' view of the ledger together, you would have a complete global state view, but no single node necessarily has the full global state view.
But no master node has that. You're not.
No.
You're just making sure that all transactions across all nodes are compatible and not double spent.
Correct.
Okay. That's all for now.
Thank you. Thank you.